when somebody enters into a SpaceX agreement with us and willing to give us their models and all for free for us to apply our methods to them, that means that they're really interested. So distributed control architecture. What we talked about till now was basically the algorithm, the logic, and we didn't talk about the control architecture. So let's want to talk about a little bit from a hardware perspective. Gas turbine engine controls, the current centralized control and its limitations, distributed engine control concept and potential benefits, some sort of a technology roadmap, some technical challenges, implications for sensors and actuators, and a summary. So gas turbine engine controls has been a lot of evolution. You know, it's the controls guys are always come at the end of the engine, right? Engine is designed, and then somebody's basic steady state performance, components are all matched, then somebody says, okay, here is the model, design the control logic such that this engine can go safely from point A to point B.
But that was only for land-based gas turbines.
Controls guys everywhere come at the end.
Come at the end?
Yeah, because we always want a model up front. So we say if we don't want a model, then it's a... So that's the control guys. So always come to the end. But control guys have been responsible or should be given credit for a lot of advancements made in the operation. I mean, like the biggest advancement made was this digital control, full authority where the pilot can move the throttle wherever they want, and this control logic takes care of it and makes sure the engine will operate safely. And before that, there were a lot of accidents because even military engines was a big problem. Because in the heat of flying, the pilot forgets that he's not supposed to put the throttle in this setting at this altitude, at this angle of attack, and boom, engine stalls and down you go. So this has been the big contributor. So they have followed a series of revolutionary development. There was the hydromechanical control, and then there was the electronic/hydromechanical control. When the electronic controls came out, people were not sure that they will work properly, so they would always have a backup hydromechanical control. And then now basically you move to a full authority digital engine control. Now it's called digital, but it's not really digital in architecture. The digital portion of that is the control law is a digital processor. There's a control box which has all digital stuff in there.
And there's still a considerable hydromechanical part in the actual operation.
And the actuation scheme is still all fuel mechanical or hydromechanical. For military engines, it's fuel mechanical. So present-day drivers compelling the next. So there's a need for more control and processing capability. Now, if I'm talking about model-based control and diagnostics, I have to have a whole real-time engine model, all the algorithms running. It's a lot of processing capability. And then you have to have additional volume, weight, and then you got to have, if you have more electronics, you have more heat dissipation requirements. More efficient engines are resulting in less available mounting envelope and a hotter environment with less capability to reject heat. Okay, so let's see if I have any chart. What do I mean by that? Okay, so, you know, originally we had some pictures. You might
I have some. In
your charts, there are... we put them in the charts, but somebody said take them out later, so we took them out later. Okay, so they're in your charts. They show the location of the FADEC. So the full authority digital engine control box, which would look something like this, we call it ECU, or FADEC sometimes is referred to as the control architecture, and ECU is the actual control box where all the electronics resides. So this box is located on the fan casing for...
First slide, you have an engine.
No,
Yeah.
It's difficult to see.
Yeah, let me just talk about it. You have your charts. Your charts show you that for the ones which show the engine and the FADEC with the guy standing, the commercial engine, the FADEC is on the casing. And for military engines, it's on the core of the engine. Core of the engine because there's not enough fan. Okay. So now, Hugo talked about two futuristic concepts for turbo aircraft engines. One is an open rotor. So if you have an open rotor, right, then where do you put the FADEC? Because the FADEC currently is put on the fan casing because that's the coolest location, right? Huh? You have to change the architecture for that. There's a reason why it is there, okay? So what I'm saying is, I'm giving you reasons why you need to figure out some way to relocate the FADEC. If because it's very interesting. So that's one thing. When you put the FedEx in a this thing, the other concept is what is it called, the gear ducted fan, GDF, which Rolls-Royce and Pratt & Whitney are fighting about right now. Anyway, so
doesn't find it.
Huh?
Rolls-Royce won't build it. Yeah.
Rolls-Royce won't build it. They have suits going against each other about infringement of patent rights. So Pratt & Whitney has developed this concept of gear ducted fan, which means a huge fan with a large bypass ratio. But the fan is so huge now that they want the casing to be lighter because it's light. You cannot build it with the same material. So they don't want the FedEx putting on the fan casing because it required reinforcing the structure of the casing. And secondly, it's like a 3-inch box. And if you put the 3-inch box on the casing, then you have the nacelle on top of it. Then the nacelle frontal area becomes too large, so you have too much ram drag. So they say, okay, can't put the FedEx on the fan casing. So where are you going to put it? So that's one big issue. And even for military engines, the FedEx is fuel cooled. So right now, the amount of heat you can dump in the fuel in military engines, the heat is being everywhere. Everywhere you have stuff, you're dumping heat into the engine. The thermal management system, there's power electronics, hydraulic systems, you're using it for fuel pumping, so everything is adding heat. The amount of heat you can add to the fuel is driven by the maximum temperature that electronics in the FedEx can operate at. So it's something like 145 degrees Fahrenheit is the maximum heat you can dump.
45? Fahrenheit? Or
Fahrenheit.
centigrade?
That one is Fahrenheit. Because it's not, you have to allow for margin. Although the electronics can operate to 150 degrees centigrade, but you got to allow for all kinds of margins. So that's what drives the amount of load you can put. They want to put more load, but they cannot because unless something happens to the FedEx. If you remove the cooling requirement for the FedEx, then we can dump more heat. So those are some interesting ideas. Control system accounts for 15 to 30% of the engine system, and weight and cost for the engine system pays the system development. Okay. Future engine technologies such as combustion flow control, they are going to be high bandwidth, and you really can't put them in the typical FedEx controls. You reach the limiting of the processing power, and typical FedEx is processing information for your 2 to 3 radians per second control for the engine. These are very high frequency things. So in engine control laws, if you build model, if you model-based control, you will need more state-of-the-art processing and health propulsion health monitoring. If you want to integrate with the controls, will make it even more complicated. So you need more and more complicated stuff in there. So that's where it is going. Now, what's the problem with the current? What is the current architecture? Although it's called a digital engine control, it's a very analog-based control architecture. There is point-to-point connection from each sensor to the FedEx. So each sensor is an analog connection. This is basically like transducers. And for pressures, you have basically taps, pressure tap tubes going into this. Because no electronics can survive the harsh environment of the engine. So all the electronics you put in this box. The power electronics is here, digital signal processing is here. They're all done over here in this box. And this is environmentally protected for, you want to use commercial electronics because the volume, because otherwise the cost. You want to gear the control towards using commercial electronics, so you basically have this big box with a lot of protection, heavy sheathing and all, to be able to operate this box. You've got to build vibration resistance. So that's the current architecture. Now, if a new sensor, somebody comes up with a new sensor and says, hey, we should put that on the engine. There's no way to put it because this is already full to capacity. Okay, and this is a box I certified. When I started designing it, I used the latest electronics. Okay, 4 years later, I certified it. My electronics is already obsolete. I already have to have a stack of buy electronics in advance to make sure that, because there won't be any producers of this electronics down the road. 10 years later, my electronics is too obsolete. Now I have to, if I want to change anything, I have to recertify the whole system. Because the whole system is all analog connected. So every 10 years or so, you would do a FedEx upgrade for a particular engine.
So if you change one of those sensors, you have to recertify the entire system?
Probably not one sensor if it's the same kind. But if you wanted to add a new sensor, which would mean you would add new processing capability in there, then you have to, I guess, recertify the whole system. I mean, you can replace the same kind of the sensor or recertify a large portion. Right? Basically, by the time you put it, you're up to capacity. All these connectors are taken out. And another portion is, do I have it in there? So this is the current centralized function. You have a sensor, you have an actuator. All the sensor basically is like a transducer. You're getting a voltage signal in there. You do all the power and signal conditioning, A to D conversion, limit checking, scaling. Then they go into control law. Same thing goes for actuator. You basically have the LVDT feedback. All your control loops are closed out there. And then you have other analog signals coming in. You do the control law processing, and that command goes to the actuators. So, okay, so these are the limitations. You have, first of all, in order to have all these wires, there's this bundles of wire going through the whole engine. So you have a heavy set of wires, very complex, and it's a reliability issue. You have many connectors in those wires. So if I have one sensor somewhere in the compressor, if I have, or let's say later, turbine area, I have a compressor, PS3 or something, in order to take that tube all the way into the FADEC sitting on the case, I have to build a wire, make it go through different components, of more holes in the components and stuff. So, and it becomes a reliability issue many times because there are many, many connectors. I think I have a number out there, somewhere around 280 or 320 like connectors and pins for the system. FADEC is built to take a hostile environment. It's very expensive and it's prone to obsolescence. And the system is very difficult to isolate faults. It's difficult to modify and upgrade. And how do you implement advanced controls in the current architecture? Because, like, if you're doing the active component control, that doesn't have to be the same level as the central control. So it doesn't make sense to put all the electronics in the box to do a component level control. You want to have your control stuff located close to the component. So the idea is then the new architecture suggested is to move to a distributed control architecture where you have smart nodes which enable processing close to sensors and local actuator loop closures. And what you do is you define a interface. Say for each component you define a common interface, and then you put all the data on a digital data bus, and that data then goes into the processing. So challenges there is to have some local electronics close to the sensing unit because you want to be able to process that signal and put it on a data bus. And you want to be able to maybe do some local diagnostics. Is this signal, is this pressure, is that sensor still good? Instead of having all your diagnostics being done centrally. So that's the concept behind it. So distributed sensor, basically distributed control, you distribute a lot of the functions. A smart sensor would have sensor-specific electronics. It has a common communication module to put data on the bus. Actuator is actuator loop closures locally, and then it puts the data on a bus, and the FADEC function is now reduced. Its amount of electronics you have to put in there is reduced because its functionality is reduced.